Assalamualaikum warahmatullahi wabarakatuh, and hope you all in a very good shape for our class today. So today we will continue our topic 2.3 3D fastener ball and screw design criteria for different types of loading. At the end of this session, students should be able first explain what is bolt tightening and preload. Second, able to calculate the tightening torque, total force on bolt and parts. Third, able to determine what is the value of factor safety for the joint. And then last, can determine the stresses value which occurs on the screw. As for the introduction, fastener is a device which can be used to join two or more members to become a one body of assembly. There is many methods can be used to join two or more members. Some of them is by using welding, or also we can use adhesive to join two parts or many parts. But for our chapter, we will only cover the 3D types of fastener. Here we have three figures. The first figure is bolt and nut 3D types of fastener. Second, we have machine, screw, and then last we have stud. These three types of 3D fastener is the most common types of 3D fastener we can see used in the machine. There is three factors we need to consider when we want to design the fastener. First, the fastener must be less weight. Second, anti-corrosion. And then third, resilient to loosening under vibration. The reason why we use 3D fastener compared to other types of fastener is, first, 3D fastener is very easy in terms of assembly and disassembly compared to, let's say, welding. In welding, we need to cut the parts in order to disassemble, but in terms of 3D fastener, we only need to drive out the screw from that body. Second, in terms of reliability, because of that self-locking effect. Third, it is very easy and cheap to fabricate. But there is some disadvantages related to 3D fastener. First is the large stress concentration happen on the thread. Second is the wear and tear, which usually occurs on the thread also. In order to find the value of tightening torque, total force on bolt and parts, also the factor safety and the stresses value on that screw, there is some value we need to find. The first value is the fruit strength, SP. Fruit strength is the axial stress at which the screw begins to develop permanent set or plastic deformation. It can be found from the table 2.2 metric specification strength for steel bolt. Here you can see the value of fruit strength on the third column. So in order to find the value of fruit strength, SP, all you need is the value of class number. Let's say given the class number for that 3D fastener is 518. So the value of the SP is 380 megapascal. If the information is not enough, maybe not for steel board, for other material maybe, we can use this formula. SP is equal to 0.9 yield strength. Next is the proof load. FP equal to SP80. AT is the minimum radial plan area for fracture through the 3D part. The value of AT can be found from the table 2.1, basic dimension of ISO metric screw thread. In this table, there is two columns to find the value of AT. The first column is for the coarse thread, and then the second column is for the fine threads. Let's say given the nominal diameter of that screw, let's say we take 10. So if the screw thread is coarse thread, so we can find the value of AT 58 millimeter square. But if the screw thread is fine threads, so the value of AT is 61.2 millimeter square. Bolt tightening is a pre-stressing at assembly, where usually the bolted joint should be tightened to produce an initial tensile force. Let us imagine if we want to tighten the nut on our car wheel. First, we will turn on the nut until we cannot turn it anymore, and then at that time usually the nut will be near to the rim. After that, we will take our universal cross wrench to tighten the nut. This process is the pre-stressing of the nut into the rim. So this bolt tightening or the pre-stressing as assembly usually been done when we want to fasten a bolt or other types of threaded fastener. This bolt tightening also can be called as preload, FI. We can determine the value of preload, FI, by these two formula. If the connection is for reuse, we can assume the preload FI is 0.75 FP, which is the preload. But if the connection is for permanent, so we will use the preload FI is equal to 0.9 FP proof load. Next, we can find the value of tightening torque T by using this formula, which is tightening torque is equal to KD FI. K represent the torque coefficient, which we will use 0.2 if the thread is unlubricated, or we will use the value of torque coefficient K equal to 0.15 if the screw thread is lubricated. D is the nominal bolt diameter and Fi is the preload, which if we use reuse connection, we will use Fi is equal to 0.75 Fp proof load. But if the connection is for permanent joint, we will use the formula Fi is equal to 0.9 Fp proof load. Usually bolt and nut are used in clamping part together. As you can see from this figure, the plates will try to move outwards, up on the top plate and then downwards on the bottom plate. This will result the bolt to experience tensile force Next, the value of total force on bolt and parts can be found from this below formula, which the value of total force on bolt FB is equal to CP plus Fi, and the value of total force on parts FP is equal to 1 minus C P minus Fi. C is the joint stiffness factor or joint constant, where the value of joint stiffness factor can be found from this equation. The joint stiffness factor is equal to Kb over Kb plus Kp. Kb is the stiffness constant for bolt, and Kp is the stiffness constant for parts. The value for stiffness constant for bolt Kb can be found from this equation, which is AB EB over L, where AB is the cross-sectional area of bolt, EB is the modulus of elasticity for that bolt, and then for L is the grip, which represent approximate length of clamp zone. As for stiffness constant for parts Kp, we can find this value Kp from this formula, where EP represent modulus of elasticity for that parts, and then D represent the nominal diameter for that bolt, and then L represent the grip, which represent approximate length of clamp zone. Next, we can find the value of factor of safety for that joint, where N factor of safety is equal to SPAT minus Fi over CP. SP is the proof strength, AT is the tensile stress area, Fi the preload, C is the joint stiffness constant, and then P is the external load. Next, we will try to see what types of stresses occurs in the threaded fastener. The first types of stress occurs in the threaded fastener is the axial stress. In power screw, axial stress can be in the form of tensile or compressive stress. But in threaded fastener, axial stress can be only in the form of tensile stress. The value of axial stress can be found from this formula, which is stress is equal to P load divided by A, area. For power screw, the value of area can be determined directly from the formula pi dr square divided by 4. But if we want to find the value of axial stress in threaded fastener, the value of A, area, can be taken directly from AT, threaded fastener, in the table. Next, the second type of stress occurs in the threaded fastener is the torsional stress. This is because power screw and threaded fastener are subjected to torsion during the tightening process. And the value of torsional stress can be determined from this formula, which torsional stress is equal to Tc over J. T represent torque, C represent the diameter of bulk, J represent the polar moment of inertia. The third type of stress is the bearing stress. Bearing stress is the pressure occurs between the surface of the screw thread and the contacting surface of nut. Let's say we have a nut here, and then we cut at the middle, and then we see from here. So what we will see is a half nut, okay, with a little thickness, and then there is area. So this area where the bearing stress occurs. The value of bearing stress can be determined directly from this formula, which bearing stress is equal to P, the load, and then dm for the mean diameter, h, depth of the thread, and ne, number of thread in engagement. Lastly, the fourth type of stress is the direct shear stress. For both threads on screw and nut, usually experience transverse shear stress. So the value of shear stress for the screw can be found from this formula, which shear stress is equal to 3P divided by 2 pi dr B and E. And for the shear stress of nut, we can directly find from this formula, which is shear stress for the nut is equal to 3P over 2 pi dP and E. Okay, that's all for chapter 2.3, 3D Fastener. Thank you guys for listening.